Good everybody, viewers out there. This is Turning Point Tutorial. We are now in the last section of the wave topic, and that is the wave cycle, angular velocity, wave number, and the general form of wave equation. The wave cycle, we'll talk about that one. Then the angular velocity, we'll discuss that. Then the wave number, we'll talk about that too, as well as the general form of the wave equation. We'll derive that. But let's discuss the first one, which is the wave cycle. A wave cycle. What is a wave cycle? A wave cycle is a trace along a wave profile between 2 points that are in phase, and therefore such 2 points or those 2 points are separated by a full wavelength of the wave profile. Once again, I take it again, that's why you'll get it clearer. A wave cycle is a trace along a wave profile between 2 points that are in phase and therefore separated by a full wavelength of the wave profile. Let me just give you an illustration here. You can consider this. Let's consider what we have here. This is a wave profile. You have, for instance, a wave profile like this, and then you talk about 2 points that are in phase. 2 points that are in phase. You can consider like this. Now you have from here, and then you move upwards and then come down, then move up again to this very point. These 2 points are in phase. These 2 points are in phase, and moving from this side up and down and back to the very place, this gives us one wave cycle. The other points, the other 2 points that are in phase here, we have this from this crest to this crest, they are in phase. From the trough to the next trough here, they are in phase. And for this reason, we always know that moving from one point to another point that are in phase forms a wave cycle. Now, look at it very well. You can consider movement from here to here, that is half cycle, and then from here to here, another half cycle. Then when you combine the two together, you have a full cycle. Then if we make an extra connection of these two, we have a full cycle. So a wave cycle therefore means a full cycle. Let's come back to another aspect here, which is very important, the angular velocity. And it is being represented by the symbol which is called omega. Angular velocity is also known as, we use omega to represent the angular velocity. Let's look at it very well now. What we should know about the angular velocity. What is angular velocity? Now, angular velocity of a wave is the ratio of the angular distance, that's the theta, covered to the time taken. I repeat, angular velocity of a wave, omega, is the ratio of the angular distance, theta, covered by the wave to the time taken. The angular distance, theta, covered by the wave to the time taken. That mathematically we have it like this. We have angular velocity, which is the omega, is equal to the angular distance, all over the time taken. Then we can rewrite everything like this: angular distance omega, angular velocity omega, which is equal to the angular distance theta all over the time taken. Let us call this equation 1. It implies that theta is equal to omega t, or call that equation 2. Now, looking at it very well, let's remember that if we go by the definition, we say here once again that angular velocity is the ratio of the angular distance. Take it from different points. Angular distance. Angular distance, whenever I see this theta has to do with angular distance, and another way we can write the angular distance, which is a theta, is equal to omega t. Then we can also say here the time too they have connect the angular distance, which is the theta, equals omega t. There are other ways we can put this angular velocity, which is theta over time. We will recall that in a full cycle, when you consider a full cycle, that is, if you look at the wave profile from this to this, from here to here, that means in a full cycle, you must have gone round an angle at the center of the cycle, and the angle at the center of the cycle is always 360 degrees. Now in trigonometry, pi is always representing 180 degrees, and for this reason 360 degrees is the same as 2 pi. So it means here that the angle at the center of a circle is equal to 2 pi radian. Call it 2 pi radian. 2 pi radian. Let's come back to what we were looking at here. For a full revolution, theta is always equal to 2 pi radians. Theta is always equal to 2 pi radian. And also for a full revolution, we have it that we should recall here that our period is equal to the time taken all over number of revolution or number of cycle, which is also equal to, now for one cycle, for one revolution, for one wavelength, we can also write it that t over 1. You can say n is equal to 1 because number of cycle is 1. For one full revolution, theta is equal to 2 pi. For one cycle, n is equal to 1 for one revolution. Therefore, we have it that capital T, which is the period, equals the time taken over number of revolutions, which is also equal to time over 1, and that gives me T. So it implies here that T, capital T, the period, is equal to the small t, the time. So if in one cycle T is equal to period and the theta is equal to 2 pi, therefore angular velocity is equal to 2 pi over here. We have the t here, and that is equation 3. Then if we do some adjustment here, we have that angular velocity, which is equal to 2 pi times 1 over period, and we recall here before that we have frequency being equal to 1 over period, and for that reason omega, which is the angular velocity, is equal to 2 pi times frequency, and that is 2 pi f. For this one, equation 4. Now we know quite well that angular velocity is same as theta over t, that is angular distance over time. Then again, the angular velocity is same as 2 pi all over capital T, that is the period. As well, we can say that angular velocity is same as 2 pi f. 2 pi f. Just take note of this, so we move forward to the next aspect. Then we also have it in mind here that when you consider another aspect, which is also the wave number, which we will know that there are other forms of terms or other terms that are connected to the wave equation. What is wave number? We use the capital K to represent wave number. Wave number is the ratio of the angular distance, theta, transversed by the wave to the corresponding linear distance, x. I repeat, it is the ratio of the angular distance, theta, transversed by the wave to the corresponding linear distance, x. Mathematically, we have this way. Wave number k is equal to the ratio of the angular distance theta all over the x, that is the displacement, linear displacement, or the linear distance. Here we have it to be equation 5. For this one, equation 5. Then it implies here that theta is equal to kx. Now, for a full wave cycle, always remember, for a full wave cycle, let's not forget that theta is equal to 2 pi radian. For a full wave cycle, theta is equal to 2 pi radian, and for that reason, we can rewrite our wave number k to be which is wave number k, which is equal to theta over x, becomes k equals the theta now is in 2 pi, then the x. Now for a full wave cycle, our distance, the linear distance, is also known as the lambda. X is equal to 1 lambda. The linear distance in a full cycle, linear distance x is equal to lambda, and theta is equal to 2 pi. So wave number becomes k, that is k equals to 2 pi all over lambda. We call this equation 6. Now the next thing to consider here is that of the combination, the new adjustments we want to make. We said that we have our phase angle, so that is our phase angle, this is theta, will be equal to kx. But now we can rewrite that, let phi be the same as, or let phi represent our theta, and for that reason it implies that our k, our theta, which is equal to kx, then becomes phi equals kx. And since phi is equal to kx, therefore phi is also equal to 2 pi over lambda times x. Hence we say that phi is equal to 2 pi x all over lambda. This one gives us the phase angle, that is the value for the phase angle, which is phi equals to kx, and same as what, phi equals 2 pi x all over lambda. Let's call this equation 7, or this one equation 7, and let this one be equation 8. Now let's move on to the other aspect, which is the general wave equation, the general wave equations. Let's recall that when you consider particles in a medium, the particles in the medium always perform simple harmonic motion, and if the motion of the particle is plotted against the displacement in form of a displacement time graph, then we have that. Let's consider something like this. If we should assume, let us see that the particles actually in that medium are all exhibiting simple harmonic motion. Then if we look at the motion and then we plot a graph, the displacement time graph for that motion will have it the very way, something like this. It's in a sinusoidal form, sinusoidal graph. Now looking at it very well, you consider that we have it that this is a vertical motion, the vertical direction, that's the y-axis, and then the horizontal axis, which is the time axis. When you consider from here to this very side, you know quite well that this is the wavelength, as is the lambda, the wavelength, and from here to this side is one full cycle. Then looking at it from the origin, the pattern we have seen here in this graph, or this the displacement time graph, is actually telling us that y, looking at the y now using the sine equation, y is equal to and this is the amplitude from here to here is the amplitude of the wave equation. Now this y is equal to a sine theta. Y becomes a sine theta, and since y is equal to a sine theta, it implies here that y is equal to, because we know that, let's recall that theta is equal to omega t. Therefore y being equal to a sine theta becomes a sine omega t, and that we know that omega also means 2 pi f, which is same as a sine 2 pi f t. So here we have it that this one becomes equation 9. Then moving forward to the other aspects, we should consider, and now we are right, and now we can write our sine wave equation. From equation 9, we have that y equals a sine 2 pi f t, but our f, the frequency, is equal to 1 over t. By when you fix this in, you have y equals a sine 2 pi. Then this here we have the t representing the f here, 1 over t, and then we have the small t, all equals a sine 2 pi small t all over the capital T, that's a period. And this is another form of the wave equation, which implies that y is equal to a sine 2 pi t over t. It's equation 10. Now there's another thing we want to consider. We want to look at another important aspect. When you consider this, you see that the wave actually starts from the origin. It starts from the origin, and the time of the rising of the wave, as well as the wave itself, the counting time, as well as the rising of the wave, all started at the same time. The rising of the wave and going up and down, as well as the counting time, they all started at the same time. That's why the wave equation becomes this, y equal to this, or this. There are different forms we can rewrite it. There are different ways we can put down this wave equation, either like this, like this, like this. But there's a case whereby the wave starts after the origin. That is, the wave now starts after the time counting time. After the time counting time, that means the time has started to count before the wave started its motion. Now let's consider this diagram here. Let's see an illustration. See the illustration now. If we have this like this, the wave rising at this very point and goes down continuously. Then let's assume from here we have the space from here, from this is the origin, and if the time starts counting and the wave fails to rise, and later on starts rising somewhere, maybe here or other points, it means that the wave rose up lately, or it came off too late. Now this time, the difference in time here, we call that the t, which is equal to x all over v. Let's all remember from velocity. You know, velocity is equal to this displacement over time. Then making your x, the t, the subject formula, it means that t equal to x over velocity, that is displacement all over velocity. And so we can use x over v to replace this very section. Now, if we consider what we have from equation 9, of the wave equation, let's recall that y is equal to a sine 2 pi ft. Now the time, there's a time difference now, and the time here is not going to be ordinary t, but what is the right t? This t here will then be the full time from the origin minus the time the wave starts rising. The full time from the origin to the very end minus the time the wave starts rising. So it means the full time, which is the t, minus the time that the wave starts rising. That one gives me the real t. So why we can now say here that t, this very t coming in here, t minus t subscript the w, then which and the t w, which also means x over v. When we replace it here, we then have y equals a sine 2 pi f open bracket t, then in tw, which is same as x over v. And when you open up everything, you will have a new expression. But let's recall that when you recall that v is equal to f lambda, recall that v, the velocity is equal to f lambda, then we can say that y equals a sine 2 pi ft minus x over v becomes y equals a sine 2 pi f t minus x over lambda. It's another form of the wave equation. Then we push it in the very way. Let's call this equation 11. Then when you open up, you have, when you open up the brackets, you have another wave equation given here, which is y equals a sine 2 pi ft minus, well, when 2 pi f multiplies x over lambda, we have a new expression there too. That will give me 2 pi f, 2 pi, this is lambda f lambda, then so we have 2 pi x all over lambda. How do you know? Because when you check very well, 2 pi f times x over f lambda, when you work it out, this cancels out, and then you have 2 pi x over lambda. But right here, let's just make progress to the next stage. This is another wave equation, equation 12. Another wave equation. Then when you look at it very well, considering what we have, we can say, if you make an adjustment, bringing out the 2 pi, factorizing the 2 pi here, 2 pi here, you have y equals a sine 2 pi open bracket ft minus x over lambda. This is another wave equation, but recall that f is equal to 1 over t. Therefore, y is equal to a sine 2 pi open bracket t over t. That means this f is being replaced by this 1 over t minus x over lambda. This is another wave equation 13. Then we can say also here from, let's call this equation 13, then this is equation 14. Then from equation 14, or from equation 13, we have the following. From equation 13, we obtain some of the wave equation 2. When you factorize 1 over lambda, factor out 1 over lambda from this, you have y equals a sine 2 pi all over lambda. From equation 13, you have f lambda t minus x here, and then consider that v is equal to f lambda. Therefore, y is equal to a sine 2 pi over lambda. Open bracket. There is f lambda also means velocity. Then you have vt minus x. This is equation 15. All these are different wave equation. You can see here that equation 11, equation 12, equation 14, 15 are different forms of the wave equation. That is in the aspect of the wave coming too late after the counting time. There's another aspect again when the wave, what if the wave actually starts very early before the counting time? It just starts its own motion before the counting time. What will be the result? When the wave starts its own motion before the counting time, then we have that we have the equation in the very form. We will have it in another form. That means it will carry this sign here will become positive. Then you have everything to become, from very beginning here, what you see from equation 11 or equation 12 or 13, or let's say from equation 12 here, let's begin on this one. Here will become positive, or here become positive, or become positive. All the signs all should become positive. That shows that the wave came up before the counting time. We will see more of this as we proceed to the next stage. Now let's consider the one concerning the case wherein the wave actually starts before the counting time. Let's consider this diagram here. If the wave, look at it now, begin to propagate before the counting time, because the counting time actually starts from the actual counting time starts from the origin. But this wave propagates before the counting time, then it means that the time that the wave starts rising will be added to the counting time, the normal counting time. So it means here we're going to make an addition instead of a subtraction. Recall that a wave y equals the wave equation y equals sine 2 pi ft. Now this t here now become this very t here becomes t, the counting time, the normal counting time, was the time that the wave spends, the time that the wave spent before the counting time. The very time tw before it gets to the origin, all be added together to form the total time. So we can rewrite it here as open bracket t plus the time that the wave started rising, and here the t subscript w is equal to x over v. It implies here that y equals a sine 2 pi f, then open bracket t plus x over v. Then when you recall this, recall that our velocity v is equal to v is equal to f lambda. Therefore y is equal to a sine 2 pi f open bracket t plus x over f lambda. By multiplication, when you expand, it implies here that y is equal to a sine 2 pi f, then t plus 2 pi x all over lambda. That's what we have as equation. Let's call this one equation 16. Let's call this equation 16. Now consider this, that in that of the former equation we normally have the minus sign in the bracket, Then for this we have the plus sign in the bracket. The first one and the other one, they are all the same, just that it's the direction of the counting time. This one here shows that the wave came up before the counting time, while the other, the wave that carries the negative sign, means that the wave came up later on after the counting time. Then we can generally put everything together as y equals a sine 2 pi ft plus or minus 2 pi x over lambda. But we know quite well that our 2 pi, but our omega is equal to 2 pi f, and our k is equal to 2 pi over lambda. Therefore, y is equal to a sine open bracket omega t plus kx. That is another wave equation we have, but this one we use it, we can say plus or minus kx. We call this one equation 17. Recall again that theta is equal to omega t, and that our kx or our phi is equal to kx. Therefore, y is equal to a sine open brackets theta plus phi. These are now equation 18, plus or minus equation 18. All these are the various types of wave equation. We have equation 11, equation 12, equation 13, 14, 15, 16, 17, 18, and even the one before equation 11, the one that has to do with the wave and the counting time starting from the origin. They are all the same as wave equation. We will now go further in our next class to discuss the calculations, different calculations under the wave equation, and how we can apply wave equation in our various calculations. We will consider that one, as well as how we can compare using the formula of the various wave equation to get our answer without stress. I believe you will be there right with us in the next class to handle cases in this aspect of calculations using the wave equation. So get ready, get yourself prepared in the next class. See you soon.